John, do you trust me in English or you prefer? Well, my name is Alex. I am PhD student number 32, I think, of John Beckman, right?
Maybe 33.
33, okay. Okay.
We lost the trail of one young woman who's in Mexico who was a student of mine.
I prefer number 33 then. So, and I had to say that, I mean, thank you, Johan, and obviously John, for giving me the opportunity to present this story, because I think this is the most amazing story that has in the history of John, probably, I know, at least that I know of. Way better than the one from the Indian restaurant. This is about airborne astronomy, and I would like to start with the very, very, very basics. This is the atmosphere of the Earth, taken from the stratosphere. What you see, this blue haze, is the thin layer of air where we all live, breathe, and allow us to fly. And it would be perfect if it was a little bit more transparent. It only allows us to see the cosmos in optical, radio wavelengths, and few other windows, because it absorbs all the photons, and that and the turbulence is the reason why we had to put the telescopes on top of the very tall mountains. Fortunately, there are not mountains of 300 kilometers on Earth, so sometimes we need to send telescopes out and out to space, and this is a huge challenge because you build a very important, very carefully designed detector, and then you put it in top of a cylinder with 5,000 tons of kerosene out to space, and things can break. So it's a little bit scary, especially for JWST. So all these telescopes allow us to see the universe in all the wavelengths that from the ground are mostly impossible, including all the telescopes that are not included there and allow us to see the sun, like SOHO or Parker Solar Probe. And this is the first protagonist of the story. Early in the 60s and the 70s, we didn't have telescopes that were used to put a coronagraph on top of that. So seeing the sun directly from the ground was extremely difficult. In case that you want to study the corona, that's a huge problem, because you're basically blinded by the light from the sun. In addition to that, you still have from the ground the problem of absorption. So if you are interested, for example, in the far infrared emission of the corona, like John was, you cannot do that directly from the ground. All the photons are going to be absorbed. So you have to be clever and try to find a way to observe the sun. And by some cosmic chance, the angular size of the moon and the angular size of the sun are approximately the same, not quite really, but that depends on the ellipticity of the position of the moon and the sun in the orbit. But some eclipses are what they are called total. So they completely cover the sun and allow you to see the corona in greater detail, including the inner parts of the corona. Why I'm mentioning the corona over and over again? Why? Because it's one of the biggest mysteries of the sun. How can you have a core that's 1,000,000 Kelvin degrees heat up, and then in the surface it's about 5,000, 6,000 Kelvin hot, and then the corona again heats up to millions of Kelvin. It should be colder. So it's for decades it's been super hard, and it's still a problem, even after Parker Solar Probe, to figure out why the corona is that hot. So one of the ideas was to observe by using eclipse and try to get better data in the inner parts of the corona. The problem with observing eclipses is that they don't appear where you want. You cannot just wait for the telescope to observe the eclipse, because it's not going to be all over your path, and they move really fast. How fast the shadow of the eclipse moves? Well, that depends on the position over the equator, but roughly 1-2 times the speed of sound. So that's really, really, really fast. On the ground, you only have about 5 to 7 minutes if you are very, very lucky to observe an eclipse in totality. By the way, this eclipse obviously was obtained from this image was obtained from space on the Rosen Space Station Mir. So the astronomers were waiting for the perfect eclipse to occur, because if you have an eclipse in the poles, they occur really, really, really fast. Plus, it's really hard to get in that position. But if you are closer to the equator, the movement of the Earth goes faster, so it allows you to have more time in the eclipse on totality, and you have more chances of doing good science. So in 1973, this eclipse was called the eclipse of the century, and everyone was getting prepared for that, because it was going to be a total eclipse. Not every eclipse is a total eclipse. It was going to be very close to the equator, so it was going to give you like 7 minutes from the ground. So it was a great moment. Everybody was getting very nervous to get the science and all these points in the map, our telescopes and scientific teams ready to obtain the data from that eclipse. So John Beckman and other teams started to figure out that this was a little bit before the 70s, that if you take an airplane and you put the telescope on top of an airplane and start observing the eclipse, you obtain better data. And if you chase the eclipse, you can gain a little bit of time. And John Beckman figured out that if they could put a telescope on top of a supersonic airplane, you can multiply by 10 the number of minutes that you have on totality. So that was the plan. Just put a telescope on top of an airplane, a supersonic airplane, not many of them in the 70s, mostly military of them. But luckily, it was the Concorde. This was the 70s, so the Concorde was still being developed. There were two prototypes, one owned by British Airways and another one by the Aerospatiale French company. So John directly asked British Airways to get the permission to use the British Airways prototype 002. It wasn't even named Concorde back then. And initial conversations went very well. At some point, they figured out that they needed to drill a hole in the very precious aircraft, and they backed out. And not to mention that they needed more holes than one, but that was a problem. So John, for some reason, the French agreed. And they joined efforts with Pierre Lena and André Touquat, which was the pilot, and many other scientists, to gather 5 teams, 5 portholes that should be installed in the aircraft. You see all these. One of them was on the side because it was to observe the atmosphere during the eclipse. And the 5 teams were selected to be from Los Alamos, the Paris Observatory, Kitt Peak, Queen Mary, University of London, and the University of Aberdeen. So they had to install all these portholes, test them, and make sure that the supersonic speeds and the lack of pressure in the outside and the huge temperatures that in the skin of the Concorde during flight were not going to put all the astronomers on risk. Also get ready for the flight plan. There was only one chance to do this. So the plan was to take off from Las Palmas at the beginning. If I recall correctly, I think that the plan was to use the airport in Dakar, but then they said that was way too risky because of the temperature of the landing strip. So they had to run all over down to Mauritania, then rendezvous with the eclipse, then accelerate to Mach 2 until totality and the shadow of the eclipse was perfectly matched by the Concorde, in which they will have the first, second, and third contact. This is basically where the edges of the moon touch the totality of the sun. And then land down in Chad after asking permission, obviously, to Mauritania, Mali, Niger, and landing in Fort Lamy 2 hours later after a planned time of totality of 80 minutes, 74 in the end because of a headwind. This is John Beckman trying with all the teams, testing all the equipment. They had very little time because the mission was approved 5 months before launch to be tested. So they had to bring all the equipment, all the teams, and try to make sure that all the electricity, the support for the astronomers on top of the aircraft, and was not interacting with the systems of Concorde. That was all between the 700 kilograms of equipment that could be bring inside. Of course, decide who was going to be on the airplane. Not everybody could be on airplane.
You can see how hard we were working.
I'm more interested by the fashion. I mean, yeah, it looks like like they were the Beatles testing something.
The second from the left has a mobile phone already.
Yeah, what is that, John? That's from the future, or?
On his phone.
Yeah. There's a fun story. I think that I may recall it correctly because I read it online, but there was a moment when I think I have a picture of this. This is John Beckman with holding. You can see all the people here is super happy because they were testing the aircraft and it worked. But John is very serious. John is in the center and is holding a helium container, like it's the baby. It cannot be away. And the reason is that they were testing. They had to bring their own helium to Las Palmas, obviously, and they had to keep it cold. Otherwise, the experiment would be gone. So they decided to put it inside of a tool shed that was owned by one of the captains of the military base. It was during the dictatorship in Spain. So they decided, okay, here's a car, but we need to put the helium inside. So they take out this car and just put the helium inside. And when they started doing that, the military came with the machine guns to say, what are you doing? Said, no, it's the helium, we are for the experiment. And they, after some while, they decided to let them do that. And that's the how crowded, and you can see how crowded the Concorde cabin was with all the crew members trying to chase down the Eclipse during one of the test flights.
You can see the hero, who's the tall guy, the pilot, the bald-headed pilot. He's the
This one. That's André Turcat, right?
Turcat.
Turcat.
He was the hero, and Pierre Lena, who was the main French scientist, is talking to him.
Mm.
Right. Okay.
Well, this is the day of the launch. John Beckman is. This is a famous picture, but I had to put it. John Beckman was trying to get very clean his own window. We had to be thankful that they remembered to put John Beckman inside the aircraft before taking off. They took off at the scheduled time with a little bit of anxious because the air controller just granted permission 1 minute before launch to another small aircraft for some reason. But they met the Eclipse and the mission was a complete success. John used this technique to hold, if I recall correctly, the mirror and the instrument with one hand, one taking all the data with the other, technique that was later developed for GAFAs. Obtained very important data about the far-infrared emission of the spicules of the photosphere of the sun. And they even had the chance to have a UFO observation, which turned out to be a meteor, but for some time they thought that maybe they were the Russians with another spy supersonic aircraft that was chasing the lead, or the UFO that came down to this cosmic opportunity to meet John Beckman. So, so the mission was a success, and after obtaining a huge amount of data, which was published in a myriad of papers, apart from the science itself, and I think that the greatest legacy of the mission was creating the base of what will become the Kuiper Airborne Observatory, SOFIA, Shuttle, and beyond. Basically putting astronomers for the first time in complete civilian science on top of the atmosphere, and making the difference between robotic and space and human exploration more diffuse than ever. And the space agencies were taking good observations of that. So here's a little video. Oh, wait. I need the sound. Sorry. I don't know if you have seen this video, John.
This film reports on a sense
Can we have?
How it works and its application to shuttle space lab operations. The airborne science of
Whatever. Yeah, we should have tested this before, right? Like John did. But otherwise, I can talk through it.
this film reports on ASSESS, a study of the airborne science.
Well, the mission, Space Agency were taking good note of what this brave team of scientists were doing, and they decided to make a new mission called ASSESS. This was again in 1975, if I remember correctly, right? And they started with the program that Galileo that was in 1973. So they were observing, obviously, eclipses the years before. So they decided that because they were building the space shuttle, it would be a good idea to train astronauts to be on the space shuttle, because now there was room for doing science. So the main idea was to put instruments.
Stop for a second. Pause for a second.
Sure.
It's because you got the sound on HDMI and not on the jack.
There you go. The audio is just fun to hear because it's all this retro audio. Let me try now.
How it works and its application to shuttle space lab operations. The Airborne Science Office is located at NASA's Ames Research Center south of San Francisco. Regular scientific flights began in 1965 when the Convair 990 Galileo chased and stretched an eclipse during the International Year of the Quiet Sun. Later, this aircraft was used for a wide variety of other applications.
So as I said, the applications were basically trying to get the astronauts and the selection program for the astronauts ready for the space shuttle. Now there was for the first time room to put scientists on top of a nice aircraft, not just military, to bring some rocks from the moon. And people like John Beckman were testing all the equipment, and not only the equipment, but also testing the people itself.
In Phase B of the ASSESS program, airborne science missions are constrained to simulate the total self-sufficiency required of these proxy payload specialists in Spacelab. One of the most realistic of these Spacelab simulations is the joint NASA-European Space Agency ASSESS mission of June 1975. During a week-long test period, the Galileo 2 represents the Spacelab orbiter combination, while a nearby complex of trailers simulates an Earthbound mission operations center. 5 men, a mission manager and 4 experiment operators continuously live and work in the aircraft and an adjoining sleeping facility while performing 5 data flights. The experiment operators selected for diversity include a scientist astronaut and a university research scientist in molecular physics, plus 2 European EOs, a British graduate student, and an infrared astronomer from ESTEC.
You know this guy?
The European Space Agency Technical Center. They must maintain and repair all experimental equipment using a standardized onboard toolkit plus spare parts and components supplied in advance. A very complex instrument on board is a French 30-centimeter IR telescope, which is coupled with a Dutch detector in one ESA experiment. Each evening, the flight crew boards the aircraft and the simulated Spacelab departs for a 6-hour astronomical mission. While no attempt is made to monitor psychological or physiological factors, conditions are comparable in many ways to Spacelab. The adjacent living module permits the crew to concentrate on their responsibilities even during off-duty hours. During the week-long confinement, 5 successful flights are accomplished.
So during this flight, they were taking off, doing experiments, and landing, and simulating all the isolation that you have in the spacecraft. So basically, testing everything that you need for building a space station. It is isolation, confined environment, risks of all types, and of course the duty of doing science at the same time while sleeping. So that was a pretty complex. This is the beginning of what will be called payload specialist later on. No, not again. Okay. However, this is, I mean, while this mission were amazing and they were also very brave, we had to mention that not all of these flights were successful. Galileo, the aircraft that you have seen is Galileo 2. Galileo 1 was destroyed during the preparations of the Concorde flight, and all the 16 people on board were killed on top of the landing strip in NASA Ames Research Center. Galileo 2 was also destroyed, this time without casualties in the same runway due to a fire. But this is a grim reminder of how hard and how riskful are these missions and the risk that involves spaceflight. Still, they inspired all these crew members, and apart from John, a very young Claude Nicollet, who later became one of the payload specialists in the space shuttle, making it a complete reality, participating in the servicing of the Hubble Space Telescope, which was the base of my PhD with John Beckman. So this is 2019, and in 2019 I asked John, hey, I want to go to NASA. And he wrote a really, really good recommendation letter. So I made it there, and when I was there, John told me, like, hey, what about magnetic fields? What if we explore magnetic fields with galaxies? And the legacy of these observatories continued with SOFIA. This time was a way bigger airplane, way sturdier, and fly almost at the same altitude as Concorde. So we started exploring the possibility of measuring the magnetic fields with far infrared polarization. Why is this interesting? Well, the idea in the 90s appeared that if you have magnetic fields that can push the gas, ionized gas, and then turn into stars, then you can have a difference between the kinematics of the gas and the kinematics of the stars. Basically, you have support by the magnetic field if it's spiral somehow, and then if it turns into stars are no longer bounded by this and will be pushed outwards. Well, its magnetic fields are not that strong, but certainly play a role in the extension of the hydrogen gas. And this is very recent simulation in 2022. So we were more motivated than ever to try to explore the shape of the magnetic field. Was it really spiral? Was it too chaotic? So how can we do that? Again, going to the stratosphere. You drill a hole in an aircraft, put a telescope with far infrared capabilities, and measure the thermally polarized radiation from dust grains that are aligned to the magnetic field in the interstellar disks of galaxies, and you obtain the magnetized maps that you can see here. This slide that I jumped was just to mention that I almost missed my flight. I was participating at the time in the astronaut selection process, and I was in the medical selection. So when I arrived to California, they told me, hey, we have a ticket for you in SOFIA. So I had to run down to the desert in NASA Armstrong to get into that airplane and pass the training of the egress, basically requirement after the fire of the Galileo 1, and the medical training. By that time, DLR already had my colonoscopy, so it wasn't very easy to pass that. So when we took off, measured the magnetic fields of the galaxies, and we made this amazing map of the magnetic fields of spiral galaxies, which basically the results can be summarized like, yes, the magnetic fields in galaxies are spiral. They are spiral inside the molecular clouds, which are way more chaotic than the magnetic fields in the halos. And they also play a role in the star formation of, regulating the star formation of the galaxies. More magnetic field, you usually have more, you have more chaotic magnetic field, you have more star formation. So I would like to finish with this and telling John, thank you very much for allowing me to be chasing you to the stratosphere and giving you a gift from your friends at NASA Ames. Thank you so much.